used by people that had to be really careful about drawing lines on a plate that was going to be used to print, you see. In thermodynamics, that's what they did. They make brass plates with all the important curves for a particular steam engine or something like that. Okay, so this has a big history, this contact business, but mainly has a wave history. So that's the thing. And if you can go this way, you can go vice versa. It's got to be a bunch of those guys to make this curve from that one. That's interesting. How's the inverse contact transformation work? Okay? So these are all things that we're going to wrestle with a little bit later on in this course. Okay? And these are not things that you would throw at sophomore physics, guys. But you should. You should throw it at them. And that's what I'm going to show you here. Now, let's just say one more thing about this before we go back to sophomore physics. The differential Ldt. Okay? And I'm putting a dt on there and on there as well. So I'm just taking the Poincare relationship, L equal P momentum dot velocity, Q dot here, not V, minus H. Okay? And looking at it. Okay? Well, what that wave thing I was waving my hands up, in front of, the momentum is h bar k. That's the de Broglie relation. It comes in 1929. Actually, it was a little earlier than that. It was like 22. But it was 1900 when Planck said E equal h bar omega. Actually, you said n h bar omega, and that's a big difference. But that is your phase, you see. That's quantum phase. That's why the LDT is so key. Now I write H up there outside, but this is what you would be doing. So that's the quantum phase differential that you're looking at, and we'll make a fuss about that, as I say, later. This is quite an extraordinary plane. It needs extraordinary proof. So we're going to be playing with this in Chapter 12 of this review unit, but Unit A is where it really takes off. Okay. Well, I'm not going to ask any questions because you should have a lot. But I'm going to take you now to a contact transformation that really deals with something that we see when we look real closely at the National Institute of Standards and Technology, the thing that generates accurate time, which reads into this nice wristwatch I bought at Walmart yesterday to replace a piece of crap I had before. In any case, what it is a bunch of cesium atoms that are sort of allowed to expand. It's a little tricky way to get them expanding as they're being thrown up into this vacuum chamber. Okay. And the idea is to have a bunch of atoms that are stationary, which you can optically read the cesium frequencies, which is our time standard that exists, for commercial use. We have that lab has much better time standards, but this is an interesting one. Or it's just a fountain. This is what we're really looking at here, is boom! And it makes an envelope, a contact envelope. Okay, and that's what we want to calculate. The shape of the volcanic plumes on Io. So here's a small example of this. This is a little bigger. Okay? And there's the plume. Okay, and there's another one. There, and there are a lot better ones that have been shown since these pictures were taken. But we're going to make our own simulation, and then I'm going to have you do some problems that involve this. Okay, okay. That's the simulation right there. We'll look at that in a minute here. Let me put the stationary object up on this screen right there. What we're going to be interested in is the algebra for just to get started here. Then we'll come back to the geometry. So I'm going to put that part up here. But in the middle of the screen, I will go ahead and let this thing, I hope, run an animation. And let's see if I can get it started here. This is, I'm trying to think, what is the name of the app?
Cool it.
Okay, this is Cool It. Yeah, right here. Okay. When I first did these things on System 9 of the Mac, and it was actually System 4 when I started this stuff, everything was based on an interface called Face It. And so I named all of the things it. Cool It, Bang It, Whack It, I mean, you name it, Quant It, they're all something it. So, you know, that's a little gross, but it's still good. There's the explosion, okay, from a point. And now the top is just reaching the highest place it can go, and there's a contact point that's on either side slithering down the parabolic envelope of all those little parabolas. And this is being done in uniform gravity. Okay? So, for what it's worth, that is the animation, simulation of that sketch over there, which came off of, that was probably System 6, with all the pixels showing. So we're going to quite often in this class do what most mechanics classes don't do, is do the mathematics of the family of curves, the whole family of curves that have contact envelopes, and understand the geometry of that. Okay? Because that geometry is pretty much what you'd get if this was a quantum simulation, except that in here there'd be all sorts of waves, and then there'd be an exponential fall off right at the contacting envelope. We've done a little bit of that, but not much. Okay, so excuse me. How does this work? Well, first of all, you go to UP1, which guys are, some of you are labbing and teaching and whatever, and get out your equations for a trajectory, one trajectory, as a function of the elevation angle and the velocity initial, whatever velocity the cannon had here. Other than that, it's uniform gravity, nothing fancy. We'll do the case where it's actually a spherical Coulomb problem, but and we'll do the inside the Earth examples of trajectories like this. But for now, it's UP1. So you've got the X and the Vx, and then you've got the Y and the Vy at time equals 0. This is what it would be as the time goes, given the initial velocity right here. That will be integrating this to a time linear, something linear in time. Okay, the velocity will be linear in time, starting out with a high positive value and dropping to a finally very large negative value. Meanwhile, this will be happening also. But one of the ways you can analyze what happens here is just imagine what it would be like if you were to get into the reference frame of what's going on here. If you did, you'd be riding up, always at the center of the circle until the circle reached the top there. The center of the circle, you can see, that's its turnaround point, and then it starts dropping. That's you riding in a space capsule or something, always seeing an expanding sphere. That's all you ever see. And that's this sphere right here. Okay? So that sphere is also contacting this envelope. And that's, you got to get all this stuff in your head before you understand what this geometry is really doing. Okay? In any case, taking these two guys together and eliminating time gives you an equation for y of x as a function of x. That's a really big luxury for problems like this, to have that function. But that's usually the hardest part of it, is to get a function like that set up. Now, I'm going to jump ahead here one step, and also over here, so you can see it from both sides of the room. Very important part. I'm taking this luxury and making immediately my generating function. Okay? So, I'm going to say S of the velocity parameter, the initial velocity parameter, the initial angle parameter, colon, and then it's a function of x and y. That's all we care about. We don't care about time anymore. Trying to figure out what's going on in space. And S equals 0 is the equation that this is. Okay, so this is, that particular generator equals 0. All right, so that is a contact transformation S of velocity 0 alpha as alpha this way. I got 45 degrees, I got 60 degrees, I got 75 degrees. I'm varying here without changing the velocity. So we're assuming that the objects have the same velocity. Now in the case of the rising cesium circle or sphere, that's a pretty good approximation, that they all came out with a particular velocity that was arranged. On the moons of Io, it's an approximation, an idealization. We're picking an average when we do that. Okay, so Io is kind of a fuzzy thing. It's not something that looks like that. But in any case, here's what we're looking at. We're looking for contact points, right? Or an equation for all of the contact points. That's, you know, that's the job of this particular homework problem. Okay? So it's the envelopes that extreme contact points with each trajectory. And each one of those is at a point where varying the alpha doesn't make much difference. As I vary the alpha, I get a lot of change here, not so much here, and then I get a lot of change down here by varying alpha. I get the range to change a lot, right? But nothing changes right here at the first order. That's the key to finding contact points, is looking for that stationary behavior. Partial of S with respect to alpha, 0. I got to solve that to get the envelope. Okay? Now, just out of curiosity, how many people have solved problems like this in a calculus or whatever mathematics course? Just out of curiosity, anybody? I mean, 20 years ago, all hands. Not anymore. You guys are being cheated. Not here. We're trying to make up for that. This is not an easy derivative. This is a sophomore problem, but this thing gets to be a mess. Not a terrible mess, but much less nice than some things. I go through and I cancel a few things from that partial derivative, and I get that. I'm still not home. I've got to feed that back into this thing to get the y envelope. But I do finally end up with a really nice result. Well, sort of nice. I got an x here. Okay, I got an x squared here, but I've got to cancel it there. I'm still not done. It really does get a lot simpler here. That's what you get. It's a parabola. You kind of guessed that, didn't you? Okay? But it's nice to see it. These extremal problems, these Feynman path techniques, that's really what it is. Feynman wrote his thesis, terrible thesis, under Wheeler, and Wheeler let him get away with it. But then he hooked up with Alfred Hibbs, and Hibbs said, hey, what's this piece of crap you have for writing? But this is really neat, let's write a book. And the Feynman path integrals then became something you could really use for certain rather neat applications. In any case, this this is a nice problem to look at. And there's a couple of examples there that are shown. And this is from Galileo, must be, and anyway, you can click on all of these and get more pictures than ones I've pasted up here. This is not NASA at its best. Coming off the NASA site here. These guys need a geometry lesson. That looks more like a fountain in Las Vegas than the actual parabolic things that you get on moons that have volcanoes. Now the thing that is going to come up here is, in order to analyze all of the pieces of that, this kite geometry really helps. So that's something, when you do this problem, please avail yourself of that. But these are basic questions that you ask about this bunch of particles. Say I have here 1, 2, 3, 4, 5, 6 different things, and I got 6 times 4 is 24 different orbits that are all going to make that kind of envelope. Okay, and it's a good idea to see if you can answer the simple questions like this. Where is the blast wave? That is, where is the circle? Where is the circle of red dots at each moment? And where is it touching the envelope? That can give you a clue where the envelope is. But in particular, we'd like to know, if we're talking about the single parabolic trajectory, you'd like to know where the focus of that is, and then you'd like to know where's the focus of the envelope, presuming it's a conic section at all. It kind of looks like a parabola, and we already calculated algebraically it was, so yeah, that makes sense. And question 3 here, how high can alpha equal 45? 45 has the biggest range, but how high does it get? It goes off and goes somewhere there. These are all questions that we look at. Now, where is the focus for this particular path? Alpha equal 90 degrees. That's pretty easy. The alpha equal 90 degrees goes boom. Where's focus? Anybody have an idea of where that focus is? Where about would be the focus of, say, 89 degrees or 91 degrees, which, let's just for the sake of argument, goes up about there. That's the way to think about the problem, right? What if it's a little off of 90? Where's the focus? And remember, I told you the focus is where the parabola slants at 45 degrees, right? And remember why that has to be, because it's the light ray coming up the axis, the parabola has to go through the focus, right? Or stated another way, light from the focus has to bounce off the parabola and go directly out on the axis. So it has to be 45, right? But what about the one that goes straight up? See, it's these limits that get a little confusing, right? So let's blow it up. Let's suppose that I blew that thing up and I got a parabola, and you know what I can do. Where's the focus? So down here, down here. So that's where you got to think, right? Where is it opposite the 45-degree slope? It's a really skinny parabola, right? It has to be really close to the top, right? And if it's straight up, it has to be at the tippy top, right? You will see that no parabola in there, right? 45 degrees, 1 pixel off the top. Okay, this is the kind of thinking that you got to get good at. Just manipulating algebra, that's crap. That can't go far. You got to think things through. This is where the fun is. Okay. Where's blast wave? We're talking alpha equal 90 degrees, but what we're talking about, it's on the blast wave of some kind. Okay. Well, It's just wherever something blown with this particular velocity v would be at the maximum. That's a sophomore physics problem right there, if there is one. And so forth. These questions get harder and harder as we move along here, asking about things. Okay. Just using the algebraic equations, you can answer a lot of these questions, but thinking them first is good. Where's the kite for this particular 45-degree thing? Where's the maximum range, right? Well, if you discover that the maximum height of 45 is there, it's going to be twice the range. But basically the idea is this thing comes off here at 45, that's got to be the tippy top, and that's got to be the place where it's 45 degrees, just like this was 45 degrees. Focus has to be right there. Right? All kinds of questions you can ask about these simulations, you see. And if that's a contact point, then there's a sphere contacting that thing, and that means that this is on the envelope right here. As you remember, the sphere is what I call the blast circle is touching the envelope at that particular time, sliding down the outside. Let's go ahead and run this again, just to see that. We'll let it run with the original thing. There's the touch point for this particular one, and then it's slither on either side as you go down. And there would be the thing slithering by the x-axis, just passing right now. And all the rest of them are going to be inside of the extended parabola before long. Okay, so there's a picture of, kind of a picture of that particular situation. Envelope, contact points, all that stuff. And this is what's really cool, we're going to see this over and over again, is the envelope contact point and the envelope focus must line up. That is, here's the focus of this parabola. It has to line up with the envelope focus. There's the envelope parabola sketched in there. And that's for the square kite. Pick some other angle. I think this one shows it pretty clearly. That may be the last. Let's see if I've got, yeah, that's where the lecture ends. You can see the ending point there. But here is a kite that goes with the directrix for the envelope. And then inside that is a mini kite that goes for a directrix for this particular point. That's kind of neat. And answers a lot of questions that are on the side here. So I'm going to give a problem similar to this one for you to chew on come Wednesday. Okay? And then we're going to do it for inside the Earth. Imagine a neutron starlet. It goes along and goes through a patch of uranium. The reason we don't have a neutron starlet is pretty obvious from nuclear physics. And neutrons by themselves, and particularly a pile of them, with beta decay, boom, electrons, neutrino, and a proton coming out of it. Okay? That would be spectacular. Okay? But we can imagine. We can imagine that a neutron starlet would hold together until it went through a patch of uranium and then it blew up. Okay? What kind of surface do you make inside the Earth? All those little tiny fragments of the neutron star. So that's something we'll tackle before too long. Okay. All right. Any questions? It's a quiet class. You've got to learn to take advantage of it. Try to make the professor look stupid. That's your job. For me, it's easy. Well, I'll say, maybe not all the time, but some of the time. Okay, we'll see you on Wednesday.